Hello, everyone. Thanks for having me here as a presenter. I am Chih-Shen, a PhD student at Texas A&M University. My supervisors are Dr. Arash Nusha and Dr. Amir Besdet. The topic I'm going to present is exploring the generalizability of deep convolutional neural networks for a post-hurricane damage assessment. Let's start with the motivation. So what is preliminary damage assessment, PDA? After large-scale disasters like hurricanes, earthquake, PDA is one of the first key steps in the process of seeking a federal major disaster declaration to assist individuals and public entities to recover. Then let me show you the flow chart for the post-disaster response. After disaster, the local and federal governments will conduct PDA. Then they will have the information about where the damage is more severe. Next, the joint damage assessment teams will be formed and assess the damage level in these destroyed areas. FEMA will then review the result and give the suggestion for presidential declaration. So why timely PDA is important to a successful disaster recovery? There are two main reasons here. First, PDA results can help estimate and quantify the damage and losses. Estimation of the numbers of uninsured houses is very helpful to the recovery process because a large number of uninsured damaged buildings may suggest a great need for additional assistance. Also, PDA can help identify any specific regions or local communities with high social vulnerability, for example, low incomes, disabilities, senior citizens. They may have been affected more seriously, maybe due to being exposed to high disaster risk or improper or insufficient disaster planning, education, and mitigation strategies. So during the PDA process, the investigators would collect the data based on the assessment form on the right-hand side. The forms are designed to be filled out very quickly and can help the investigators to easily determine the damage state of each building. Also, there are quantified values to help the investigators to determine the damage state. The forms are actually based on FEMA's manual, which is shown on the left-hand side. There are 5 damage states defined by FEMA, rating from 0 to 4. The damage level increases with the damage state, and the description provides a simple explanation and quantified values to determine the damage state. So, for example, if we see the second row, which is the damage state 1, the roof cover value is between 2% to 15%. However, depending on the size of the affected disaster site areas, PDA by traditional ground crews can be very time-consuming and resource-intensive. Therefore, our past research has introduced the use of deep neural networks and remote sensing technologies to perform visual damage assessment to improve the quality and the speed of PDA, as shown in the video below. In this work, we aim to evaluate the generalizability of the developed deep neural networks and explore how success of the deep learning applications for aerial PDA can be quantified and benchmarked on other disasters. Let me introduce the deep learning framework we propose for damage assessment. Unlike many computer vision tasks that involve detecting everyday objects, for example, dog, cat, car, people, post-disaster scenes are very complicated, and this could cause a relatively large number of false detections which will worsen the model performance. So we propose a double stack model to address this PDA task. As shown in the figure below, in phase one, model L will locate buildings of input images. Then in phase two, model C can use the copied images to classify the damage level. And damage C is architect based on, model L is architect based on RetinaNet, and model C is based on MobileNet. They are both deep learning models. To explain more clearly, the input will be like the top figure on the right-hand side. Next, the model L can detect the location of the buildings, which are covered with boxes. Finally, model C can classify the damage level of each building. The CNN was trained on DorianNet dataset, which is a visual dataset from Hurricane Dorian in 2019 for post-disaster damage assessment using UAV imaging. And this study creates and utilizes unseen in-house dataset from three past hurricanes, namely Hurricane Harvey, Maria, and Irma, to evaluate the performance of the trained CNN models. This data's description is shown in the table on the right-hand side. Here is the model testing result on these unseen disasters. First of all, the localization model, model L, was trained and tested on Hurricane Dorian videos, resulting in 63.3 AP, and testing this model on new footages from Hurricane Harvey, Maria, and Irma without retraining the model yields AP values of around 45%. A closer investigation led us to attribute this lower but expected performance to the factors of different building types, terrains, and other scenes characteristics visible in original Hurricane Dorian used for training. But clearly, as more diverse of the training data is collected and used, it is expected that the quality of the model L will increase. For model C, it was trained and tested on Hurricane Dorian again. It has overall 55% accuracy. And if we test this model on new footages from Hurricane Harvey, Irma, and Maria in table one, a previous table, without retraining, the accuracy is around 43%. The table below summarizes the performance of Model C, expressed in the terms of accuracy and the square of EMD square, the square of Earth's mover's distance, when tested on Hurricane Harvey, Maria, and Irma videos. Results contains a wide range of values obtained from both metrics. And these performance measurements are slightly lower than, but relatively similar to the testing result on the training footage, which indicates that the model have a good performance of generalizability across disaster events and locations. After talking about the result of the generalizability of AI-based damage assessment, the next question is that can AI users be informed if the uncertainty of the model is very high when making the prediction? And this uncertainty information can be very helpful for the decision making. So one of our ongoing research is to create an uncertainty-aware deep learning using Bayesian inference for damage assessment. The input of the CNN model are built-in images, and the output is the SOMAX distributions with confidence intervals. So this can help us to rigorously quantify the uncertainty of the damage assessment result. as shown in the figure on the left-hand side. So we also resent the CNN attention zone using class activation mapping (CAM) techniques. Interestingly, it is noticed that the trend CNN tends to classify the damage level based on the roof conditions. For example, the roof cover damage, roof deck damage, which is actually, this behavior is consistent with the human annotators. Also, we compare the prediction performance to the 20 crowd annotators as shown in the figure on the right-hand side. By looking into the last column, which shows that the result from human annotators. These figures show the various opinion on the damage level determination from aerial images. Moreover, comparing this deep learning performance with humans, the third and fourth column, the result generally shows that a strong consistency between the CNN prediction and the overall human decision by looking into the CNN damage prediction and ground truth. In summary, we deploy a stacked CNN architecture for building localization and damage classification, including Model L and Model C. The models in this study initially trained on aerial footage from Hurricane Dorian and was tested without retraining on unseen footage from several other hurricanes. Analysis of the results showed that the building localization neural network, Model L, reaches 45.2 precision, while the damage classification model, Model C, achieved an overall 43.1 accuracy on scene video. The result generally indicates that the models have good performance of generalizability across disaster event and locations. And I'm near to the end of the presentation. I'll be very happy to answer any questions you may have. Thank you very much.